So today I want to discuss another problem, deep learning. Over the last few years it has picked up massively, right? Everybody wants to do deep learning. It's shown very good results on images and videos, but the issue is that people are becoming really ambitious, right? And again, the sizes of these models are really exploding. So the number of parameters are in millions now that people are dealing with. As you increase the number of parameters, the training, you have to train these networks, the training becomes more and more computationally intensive, right? And you have a lot of data as well. And as you know, right, when you train, you have to train the entire data. So you have lots of data, you have lots of parameters, and the end result is that you have a problem which is taking weeks to solve on a single node computer. So again, you use parallelization over here, but let's understand how you use parallelization, right? So I'm not going to go into what neural networks are, but let me just try to give a very high level overview of what we're trying to do in deep learning, how the process works, and we are primarily going to concentrate on batch gradient descent, right? That's the part that we want to parallelize, the batch gradient descent. So how does deep learning work? You have some non-convex topology, right, and you want to find the minima, right? You have some cost function. The traditional way to do it is gradient descent. And how does gradient descent work? So there are many variants of gradient descent, right? So how does it work? Well, let's say that you are at a current point in the topology, right? So what does it do? You take one input, maybe it's an image, maybe it's a video, whatever. You take one input, you pass it through the network, and then you do something called back propagation, not important. What is the crux? The crux is, at the end of the day, you are computing the gradients del C by del W, where W is the weights or the parameters of the model, right? And C is your cost, right? So this is the gradients of the cost with respect to the current image, right? With the current input that you've passed. The gradients basically tell you what is the slope at the current point where you are at, right? And once you know the slope, you basically, what does gradient descent method do, right? It basically just goes down the slope, right? And of course, it's a challenging problem that how much of a jump do you take, right? That's an interesting problem. Again, we're not going to get into that, right? But essentially, you take a jump in this direction, maybe a certain step size, and you reach a new point over here, right? And then again, you compute the gradient over here, and so on, right? You keep on doing that until you reach some local minima. Gradient descent works for convex problems, but we are in the non-convex world, we don't have an option, we don't know any efficient method, so we apply the same technique. And there are ways of carefully doing the gradient descent so that you don't end up in a bad local minima, right? They're all heuristic based, but yeah, they work fine in practice. The crux is you want to do gradient descent, right? And in deep learning, you don't want to take one input at a time and pass it through the network because there is too much noise in the gradient that you get. So you don't want to take one input. What is the problem with taking one input? Too much noise, right? Another option, take all inputs and compute the gradient, right? And what is the problem with that? Well, you're doing so much computation just to figure out one gradient, and then you're going to take one jump, and it's a terribly slow process, right? So what is the midway? The midway is you take a batch of inputs. And if you take a batch of inputs, the batch size is important, right? What is the batch size you're going to take, right? So it turns out quite fine. You take a reasonable batch size, it approximates the gradient quite well, and you get pretty good results, and you're making progress in every step. The larger batch size you take up to a certain limit, as you increase the batch size, you get to the minima quicker and quicker, right? After a certain point, increasing the batch size doesn't help too much. But again, let's concentrate on the lower batch sizes. So typically nowadays, people are doing this deep learning training on GPUs and so on, and for some complex networks like GoogleNet and ResNet, right? So you can run batch sizes of, something of the order of 32 on a single GPU, okay? So now, if I tell you that you have, let's say, 100 nodes or 100 GPUs, how are you going to scale this? What can we possibly do to improve this batch gradient descent method? That is the question we want to deal with. So one the simplest thing that you can think of is just increase the batch size, right? So that is called data parallelism. And that is the simplest way employed, but it leads to challenges, and we'll talk about those. So how do you do data parallelism? Well, you just increase the batch size. Instead of 32, let's say I'm going to work with 320, right? I employ 10 GPUs, okay, 10 nodes. So you have 10 nodes, each node is doing, let's say each node has 1 GPU, so each node is doing a batch size of 32, and you have 10 such nodes. So what does that mean? Each node is picking up 32 inputs, 32 images, processing them, computing the gradients, and then what do you have to do? So let's come back to batch gradient descent. How do you compute the gradient in batch gradient descent? Let's say you take an input of size 32, right? You compute the gradients for all the 32 images independently. So you have 32 sets of gradients. And then what you do is you basically simply add up the gradients. In batch gradient descent. Actually you take the average, right? But the basic operation you're performing is addition. So we want to average up all these gradients and then go in that direction, whatever the average direction is, right? The average gradient direction. So what does that involve? That involves that you have all these gradients of 32 images, you basically add them up and divide. The complexity over here, division is straightforward, the complexity here is addition. How do we add them up? So on a single node it's straightforward, you just add them up. What about in parallel? So what do we want to do? Well, we have 32 inputs here, 32 inputs here, 32 inputs here, and we want to add these up, right? So locally I can add up these 32, that's not an issue, right? Each node can add up its own 32 sets of gradients. Remember, what is one set of gradient? It's the set of the gradients for all the parameters with respect to the cost. If there are million parameters in the model, it will be a vector of size 1 million, right? Okay, so first you do a local addition, that's straightforward. Okay, what is the next step you have to do? Well, I want to add up across all of these, right? I want to add all these up. And then division everybody can do like quickly, that's all. Where do I want the result?
Any of the nodes?
All the nodes. I want it back on all the nodes. Why? Because when each node processes the next batch, they want to work with the new updated weights, updated model, right? So I want this result to be available back on all the nodes. Once all the nodes have the sum, they can do a local division to get the average, right? And once you do the local division, you can just update your weights, right? What is the weight update? That is basically you have a set of weights and you say weights goes to weights plus some step size times the average gradient, average delta W, right? That's the average gradient. Okay, so this is again local. This is straightforward as long as you have the entire sum. So we are going to deal with the summation problem. So what's the crux? The crux is that we want to perform this operation. What is this operation? I have a vector, a large vector on each node. I want to do element-wise addition of all these vectors and I want the result to be available on all the nodes. This is called the all reduce operation.
So what is average delta W? I mean your...
So I have a vector W which is W1 to Wn, right? This is the set of weights you have. Let's say I have one input I1, another input I2, I have another input I3. When I do a forward pass and a back propagation on I1, I get a set of gradients, right? So I get some delta W1, delta W2, delta Wn. I get the gradients with respect to input I1. Similarly, I get gradients with respect to input I2, right? Maybe I need another index to say that this is for I1, this is for I2 and so on, but yeah, I don't want to make things too complicated. I3 and so on. So I have a gradient of 1,000,000 parameters for each input. I want to average all these gradients. I want to use the average of all these gradients. That's what I'm calling the average delta W, which is again going to be this delta W1 I1 plus delta W2 I2 and so on, right? Of course, divided by the number of inputs. Okay, so this part is clear, right? So we are dividing the inputs. We are increasing the batch size, which means that the number of inputs increases. That is divided amongst the nodes. And finally, you are going to accumulate the gradients. Each node has a gradient which is the size of the entire model, all the parameters in the model. Okay. So what is the operation? Yeah, we were discussing the operation. The operation we are interested in is all reduce operation, where you have large vectors on each node and you want to add them all up element wise, and the result should be available on all the nodes again, right? So this is the interesting part. This is where the systems or the parallelism aspects come in deep learning, and this is very, very critical, right, for the performance. As you grow to large number of nodes, this all reduce becomes your issue, right? And it also depends on the network. If your network is weak, you're in more trouble, right? It's going to be even slower. Okay, so how do you perform an all reduce operation on a network? Let's take a simple example, right? I have a set of nodes which are just connected point to point with some links. Okay. What is an efficient way of performing an all reduce operation over here? Or let's break it down, right? All reduce is actually slightly complicated. It's probably the most complicated of all the MPI collectives, right? So let's start with something simple. So there is one way of doing all reduce, one simple way of doing all reduce. That I'm not saying that's the most efficient, but let's start with that. So what is one way of doing all reduce? You do a reduce followed by a broadcast, right? What is reduce? Reduce is simply, you say that I'm going to take the element wise sum of all the vectors and accumulate it on one node, a node called the root. I don't want the result on all the nodes, I want it on a single node, okay? So that's what the reduce operation is, and broadcast is basically just saying that I have some values and I want to send it to all the nodes, right? So you have a vector W here, W5, W4, these are all vectors, W3, W2, W1, W0. So how do I do a reduce? So W5 can just send its vector to the W4, right? W4 can add its elements, do the element wise addition into the vector and pass it along to W3. W3 can do its own element wise addition and pass it to W2 and so on. And what will you get at the end of it? What will W0 have? That's called the reduce operation. It will have the element wise sum of all the vectors. So we'll actually be going through all this a little more formally, but in the first few lectures I just wanted to give you some motivation, right, for where all we apply parallel programming and what kind of things we are going to study. Okay, so this is element wise sum of all the vectors, and now this is available on W0. Now what do? Well, I want it on all the nodes, so I do a broadcast. What is broadcast? I just send the entire final result vector to W1, it forwards to W2, W3, W4, W5. That's the broadcast. Okay, and everybody has all the nodes. Is that the most efficient way of doing it? No, right? And that's what we'll study in this course. And interestingly, fortunately or unfortunately, whatever, these operations, the performance of these operations depends heavily on the topology that you're using. And for every topology, you have to design a different algorithm, okay? You can't just design an algorithm which works for all topologies. So people have done that so that people have a starting point. That's not performance optimal, okay? Just to illustrate the point again, right? Suppose that I have this, let's say a linear array again. And let's say I have a vector of size n. I'm just going to deal with a very simple operation, broadcast, that's it. Okay, let me start with something very, very simple. I just want to broadcast a vector of size n to all the nodes. And suppose that the bandwidth of every link is b. What does that mean? It can transfer b elements, words. Let's suppose that each element of the vector is a word size. So it can transfer b elements on the link per second. Right? That's what we are saying is the bandwidth of a link. Okay. So first I broadcast from W0 to W1. Right? How long is that going to take? N by B? Yeah. And let's not deal with ceiling floors right now. Let's just keep it simple. N by B, and then W1 will transfer it to W2, to W3 and W4 and so on. So it's eventually going to take time N by B times number of processors minus 1. Right? If there are P processors, there are P minus 1 links. Right? So it's going to take N by B times P minus 1, roughly of the order of, let's just approximate it, NP by B. Right? That's the number of seconds it's going to take. Let's just see how topology affects an operation like broadcast. So one very, very simple thing that one can do is add a wraparound link. So we are throughout going to assume that all links are bidirectional. Well, even if links are bidirectional, for the basic broadcast, without this wraparound link, you can't do anything else. It will still take NP by B time. But what if you have the wraparound link? Can you do something different? Here is what you do. You divide the data into two parts. One data stream will go down this path, and the second data stream is going to go down this path. It's going to come here, 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 and here. Okay? So remember, this is the root, right? This is the guy who has the data that needs to be broadcasted. Clear? So now how long is it going to take? Roughly half the time, right? You can see that. Your data is now n by 2 in the right direction and n by 2 in the left direction, but that's happening in parallel. So n by 2b, right, times p minus 1, approximately np by 2b. Okay. Now let's look at the topology a little bit more. What else happened with the topology? Suppose that I have a 2D mesh. So I can arrange my nodes as a 2D mesh, right? For simplicity, let me assume it's an root P by root P mesh. Okay. So this is a 2D grid or 2D mesh. So this is the topology. So we are going to talk about theoretical topologies also, but we are going to focus more on topologies which are really used in computers today. Okay. So 2D, 3D, 5D torus grids are actually used in supercomputers today. Okay. Then we are going to study, from a theoretical perspective, we are going to study a few topologies like cliques and hypercubes, which are again important to understand the theory, but they are not used in practice for obvious reasons, which we'll discuss. So we'll concentrate more on networks which are practical and actually used, right? But we will still cover other theoretical networks in order to gain a theoretical understanding. For simplicity, let's say my root is this one, right? So now how will it do the broadcast? So how many parallel paths can I have? So what was over here? I mean, the whole issue here was that I was able to set up two parallel paths which had no link contention. What does that mean? That they were not using the same link in the same direction, right? So I was able to set up two paths which were not having any link contention, and therefore I was able to pass half the data here and half the data here. So if I am able to generate three paths, then I can pass 1/3 the data and get the time down to 1/3, right? And 4 paths and so on, right? What can we do in a 2D mesh? Can I do something smarter? We can start with the most obvious stuff. Yeah, this is one way. If I send it down here, now can I set up two paths? Can I set up two paths? This is one path, right? It's not a path, it's a tree. So I want to set up a tree. Basically, what is a broadcast? From one node, you set up a tree which basically reaches all the other nodes, right? And then you send values down and it gets broadcast down the tree to all the nodes, right? So this is one tree which is reaching all the nodes. Can I set up another tree? Maybe I can modify this tree slightly and then maybe I can set up another tree.
But the minimum distance would have to be traversed, right? I mean, one path should at least be as long as the height plus length plus width.
Yeah.
So I mean, that will be the bottleneck even if we find other paths which are.
So there are other things that we didn't discuss, which we'll discuss finally. That is that you can interleave data, right? So if you have a huge message that you want to pass, so let's discuss that first before we come here. Maybe we can discuss this next time. But let's go back to this network, right? Let's go back to a linear network. So I was broadcasting a value from W0 to W1, W1 to W2, W2 to W3, W3 to W4, right? Now, if I have a very large message which I want to broadcast from W1 to W4, I'm not going to send the entire message from W0 to W1 and wait for W1 to receive the entire message and then W1 starts sending to W2, right? That's not a very wise thing to do, right? Because I'm wasting all the time. W1 has some data, but it's still waiting for data to come from W0, right? So what we do is we typically, if we have a very large message, we typically divide it into chunks. Okay, we divide it into small chunks, and as we said, right, like applications like deep learning and even matrices that we're talking about, the data that we are trying to broadcast or do is very large, right? So therefore, this technique works well. So what am I going to do when I split it? So let me call these packets, right? P0, P1, P2, P3. So first I'm going to send P0 to W1, okay? Think of it as iterations or steps, right, of the algorithm. Now, in the second step, what's going to happen? W1 is going to send P0 to W2. At the same time, W0 is going to send P1 to W1, right? You get it, right? What's going to happen next? Well, in the next step, it's going to send, W2 is going to send P0 here, while P1 here, and this sends P2 here, and so on. So you basically divide the data up and send it in chunks. So that's normal practice. This calculation that we did was assuming that W1 waits for the entire data to come and then sends it forward, right? That's what we were assuming over here. So in that respect, right, this is in some sense, it's not very clear whether this is latency or bandwidth, but yeah, it's a combination of the two, right? That's the total time, but whatever it is, latency or bandwidth, this is the total time it takes for the operation to complete. That's what this is. So how did we improve that over here? We divided the data into two parts, and then half the data we sent down here, half the data we sent down there. That brought down the total completion time by a factor 2, right? So the question is, irrespective of what the distance, max distance is, what do I want to do? I want to just minimize the total time it takes to complete this operation. How do I construct the other tree? All the data resides at the root, right?
Yeah, I mean, starting from the root, the first one line goes.
Tell me the first direction. Where is the first line going? It's not so clear to me. Down?
I mean, yeah, goes down.
But that link is already being used. Can you see that? The blue tree is already using that link in that direction. Is it clear? There is link contention over here. The blue tree is already using that link in the same direction. If it was opposite direction, I would be fine, but this is in the same direction. So I can't put the green link over there. So let me just tell you two quick solutions, right? One is a fancy solution. Let's see how that works. Yeah. So here's what I'm going to do. I'm not going to use that blue link. Instead, what I'm going to do is I'm going to send data here. It's still a tree, and it reaches all the nodes. Now I have these links free. Now what can I do? Now I can send data down here for the second tree, right? And it can go down here, it can go down here, it can go down here, and from here you go back up here. And you can verify that no link is being used in the same direction, so this is contention free. Okay, so you are able to actually, there's another way to do it, right? What is the time it takes to do this operation now? Sorry, let's calculate that first. So you're sending half the data over bandwidth B links, and how many hops does it have to take? It has to take roughly about 2 root p, right? 2 times root p minus 1, but let's approximate it. 2 root p, is that okay? Which is what? Which is 2 cancel out, n root p by b. All right. Let me give you another solution which builds on the previous solution. So here's another fancy thing we can do. So what I'm going to do is carefully look at this. What is this doing? This is overlaying a linear array. We already studied linear arrays, right? This is just overlaying, embedding a linear array on a 2D grid, right? And once I complete this part, it's the torus, the wraparound link is also there. And now I can again use it in two directions. Okay? So this is simple embedding that I can use. But this is not so good. Why? Because what is the cost over here? So I can send data in both directions. So I have n by 2 data over links of bandwidth b. But what is the number of hops to complete the entire operation? P. Roughly about p. This entire path is very long. I have to traverse this entire path. So np by 2b. But p is much larger than root p, right? So it's not so great. Okay, this is the kind of stuff we'll be talking about, right? How to optimize various MPI collectives on various different architectures, and we'll deal with architectures which are being used today. Okay.